Let's take a look at question 15. So question 15 says, check linear independency of the following. Check if these are linearly independent. So f1 is equal to x, f2 is equal to x squared, and f sub 3 is equal to 4x minus 3x squared. Very good. By looking at these functions, you can check the ratio. If the ratio is equal to a constant, then you can say that, hey, they are linearly dependent or not. So the division between these two, you get x squared over x, which is x. The division between 4x minus 3x squared divided by x gives you 4 minus 3x. The division between 4x minus 3x squared over x squared gives us 4 over x minus 3. Let's check the combination of these. So, for example, if I take this function, 4x minus 3x squared, and form a combination, linear combination of these two, 4x minus 3x squared, becomes 1, which is constant. So it means that they are linearly dependent. You might be interested in finding C1, C2, C3. So this is method A, method B, C1x plus C2x squared plus C3 4x minus 3x squared. This guy can be written as, well, C1x plus C2x squared plus 4C3x minus 3C3x squared. So by taking like C1 equals to -4 and C2 as 3 and C3 just 1, we see that the linear combination becomes 0. So in another method is just by investigation, finding C1, C2, and C3. Another method is using the Ron scan. The Ron scan of these three functions, f1, f2, f3. Here you have three functions, so you get up to the second derivative, x squared, 4x minus 3x squared. You get 1, 2x, 4 minus 6x, 0, 2, -6. We have x parentheses -12x, and here you have -2. Let's just distribute this, -8, and plus 12x, then minus x squared times -6 plus 4x minus 3x squared times 2. So this guy becomes, let's simplify this, you get -8x plus 6x squared plus 8x minus 6x squared, which is obviously is 0. So either find or form different ratios with different combinations, and then we can find C1, C2, C3, and finally finding the Ron scan. Let's take a look at question 20. For question 20, we have the following. These two functions are given to us. So we have f1, which is equal to 2 plus x, and f2, which is 2 plus absolute value of x. So we have these two functions. What are we going to do? We're going to try to break down the absolute value. The absolute value becomes, well, if x is greater than equal to 0 becomes x, so you get 2 plus x, right? And if x is negative, we get 2 minus x. So we are just comparing these two, check to see if they are linearly dependent or independent from each other. Very good. So if we just try to form different combinations and check to see if the ratio is a constant or not, 2 plus x divided by 2 plus x is equal to 1. But the absolute value 1 has two definitions. We cannot just rely on 1. We have to divide this by 2 minus x as well. 2 plus x divided by 2 minus x, which is not a constant. We can take any other linear combination. Since these two are different from each other, any division forming any ratio doesn't give us a constant for both of the cases. So by looking at the ratio, you can say that, hey, it seems like they are linearly independent from each other. Let us try to find C1 and C2. C1, 2 plus x, plus C2, well, F2, 2 plus absolute value of x. Again, this guy has two definitions, 2 minus x and 2 plus x. So obviously here, if you want to simplify this, we cannot just leave it as it is. It means that if I write it as C1, 2 plus x, plus C2, 2 plus x, we have to at the same time consider this case, C1, 2 plus x, plus C2, 2 minus x equal to 0. So you have a system to solve. Can you find any C1 and C2 that satisfies these two equations? No. So based on our investigation, you can also check their graphs. They are going to be linearly independent. They cannot be multiples of each other. Just take a look at the graphs. The graph of 2 plus absolute value is just a shift, vertical shift, 2 units upward, and the other guy is just 2 plus x, which is going to be this portion. There is no way these two be multiples of each other. This is 2 plus x, and this guy is 2 plus absolute value of x. So they are linearly independent. Question 25 is also the same. It said check to see if you have fundamental set or not. So it means that we need to show that if they are linearly independent from each other or not. So for question 25, we have the same method. Here you already have the differential equations. The second derivative of y minus 2y prime plus 5y equal to 0. And one of them is f1 or y1, which is given to us as e to the x cosine of 2x, and y2 is given to us as, well, e to the x sine 2x. You don't have to be worried about the interval because all of these functions and the constants are continuous on negative infinity to positive infinity, going back to pre-calculus and algebra. So to check to see if they are linearly independent from each other, first of all, we can form the ratio. y1 divided by y2, it's e to the x cosine 2x divided by e to the x sine 2x, which is not a constant. Or you might be interested in finding C1 and C2 cosine 2x plus C2 sine 2x equal to 0. C1, C2, try to find C1 and C2 that make this linear combination to be equal to 0. You cannot find one. Or you can find the method of Wronskian of these two functions. This guy guarantees and assures us that these functions are linearly independent or not. Here you get y1, y2, e to the x cosine 2x, e to the x, sine 2x, and then here we have to take the first derivative of these two, so I need more space. For this guy, we're going to apply product rule, e to the x, cosine 2x minus 2 e to the x, sine 2x, and for this guy, we get, let me move this a little bit here, we get e to the x, sine 2x plus 2 e to the x, cosine 2x, and the determinant becomes e to the x, cosine 2x, parentheses, e to the x, sine 2x, plus 2 e to the x, cosine 2x, minus, now the multiplication of e to the x, sine 2x, parentheses, e to the x, cosine 2x, plus 2 e to the x, sine 2x. Let us simplify this. So here we can factor out e to the x, and then we get a factor out e to the x from all of this. Actually, if you multiply this, you get e to 2x. So let us factor out e to 2x. We get cosine 2x times sine 2x plus 2 cosine squared of 2x. And here we have minus sine 2x cosine 2x plus sine squared 2x. Well, obviously, these two are opposite of each other. And okay, let me just put 2 here. You get e to 2x, and we have 2. You can factor out 2, and we get sine squared 2x plus cosine squared 2x. This is just 1, so you're left with 2e to 2x, which is never 0. So Wronskian is not 0. It means that they are linearly independent, or these two functions form the fundamental set for this differential equation. What's the meaning of that? It means that any general solution can be written as, so general solution can be written as C1 e to the x cosine 2x plus C2 e to the x sine 2x. General solution. On negative infinity to positive infinity. The same for question 30. So question 30 says, we have the following. We have the fourth derivative of y plus the second derivative of y equal to 0. You have 1x cosine x and sine x. Guys, note that here we have 1, 2, 3, 4 solutions for this fourth order linear differential equation. So the very first step is to try to just divide this up and try to see if we can get a constant for the ratio here. 1 divided by x, or x divided by 1, cosine x divided by x, sine x divided by cosine x, sine x over x, and so on. We can just form all of these possible combinations of the ratio. You can just combine 1 plus x, sine x plus cosine x, and the rest of them, and none are constant. Or you can try to find C1 times 1 plus C2 times x plus C3 cosine x plus C4 sine x equal to 0, and try to find these coefficients C1, C2, C3, C4 that makes this linear combination equal to 0. You won't be successful. And finally, the last step, the last method, the last option that you have is forming the Wronskian of 1, x, cosine x, and sine x. Here we are dealing with a 4x4 matrix. We're going to copy down 1, x, cosine x, and sine x. Their first derivative, 0, 1, negative sine, cosine, and the second derivative, 0, 0, negative cosine, negative sine, and the third derivative, 0, 0. Here you have sine x and negative cosine x. Now we need to find the determinant of the Wronskian. Here you have 1 times, I need more space, just move this up a little bit. So here you have 1 times the determinant of 1 negative sine x cosine x. I'm working with this matrix here. 0 negative cosine x negative sine x, and here I have 0 sine x minus cosine x minus x times the determinant of 0, 0, 0 negative sine negative cosine sine and finally cosine x negative sine x and negative cosine x. Then we move to cosine plus cosine x and the determinant of this matrix here 0, 0, 0. Then here you have 1, 0, 0, and then you have cosine x negative sine x negative cosine x and minus sine x times 0, 0, 0, 1, 0, 0, and then negative sine x, negative cosine x, and sine x. So you can find the determinant of each of these. This becomes 1. Well, the determinant of this guy is 1 times, here you have cosine squared, and then even 1 cosine squared of x, and here you have plus sine squared of x. Minus minus sine becomes sine, and then the determinant is 0. Plus cosine, then the determinant is 0. So we don't need these terms. We don't have enough spot. And here you get minus x. Well, this is 0, becomes 0, and then you have negative sine. The determinant is 0, and then cosine, the determinant is 0. So you have another 0, plus here you have cosine x, here 0 times the determinant is 0, and you have 1 times the determinant is 0, and then you have cosine x, the determinant is just 0. And finally, you have negative sine x. Well, again, the same process, 0 times the determinant is 0, 1 times this determinant is 0, and then you have 0. So as you can see, here you're left with just 1, which is not 0. So since the Wronskian is not 0, it means that this set is linearly independent. You have a fundamental set, 1x cosine x and sine x. We have general solution y as c1 plus c2x plus c3 cosine x plus c4 sine x. General solution for this differential equation. Let's take a look at 35. So question 35 says, you have the following differential equation: the second derivative of y minus 6y prime plus 5y equals to negative 9 e to 2x. It says check to see if y sub p1, which is 3e to 2x, is the particular solution for this differential equation. Okay. So for this guy to be a solution, it means that it must satisfy the left-hand side and right-hand side. So what is the left-hand side of this differential equation? We have the second derivative of this guy, the first derivative, and then plug that in. So the first derivative of this solution is 6e to 2x, and the second solution becomes 12e to 2x. So we have 12 e to 2x minus 6 times 6 e to 2x plus 5 e2 times 3, so we get 15 e to 2x on the left hand side. On the right hand side, we must have negative 9 e to 2x. This is my right hand side. And to check to see if left hand side and right hand side are equal to each other. So here you have 12 e to 2x minus 36 e to 2x plus 15 e to 2x. Well, if we add these two, we get 27 e to 2x minus 36 e to 2x. Well, it is equal to negative 9 e to 2x. So we just showed that this guy is a particular solution for this differential equation. The second differential equation that you have is written this way. It is the second derivative of y minus 6y prime plus 5y is 5x squared plus 3x minus the 16. And it says, hey, you have a particular solution, which is given to you as y sub p2, which is x squared plus 3x. So we have the first derivative, 2x plus 3, and the second derivative is 2. Just plug in to the left-hand side and right-hand side. So we're not worried about right-hand side, it's just a quadratic expression. So the second derivative, 2 minus 6 times 2x plus 3 plus 5 times x squared plus 3x. This guy becomes 2 minus 12x minus 18 plus 5x squared plus 15x. Well, if we simplify this guy, what do we get? We get negative 16. Here we have plus 3x plus 5x squared. So as you can see, left-hand side and right-hand side, which is this guy here, are equal to each other. So we have a particular solution for this differential equation. Now for the part B of the question. Part B of the question says, well, now find particular solution for the second derivative of y minus 6y prime plus 5y equals to 5x squared plus 3x minus 16 minus 9 e to 2x. Okay, let's just compare this differential equation with the given differential equations here. You have negative 9 e to 2x. Negative 9 e to 2x. It appeared here. And then you have 5x squared minus plus 3x minus 16, which has also appeared here. So we have a combination of these two functions on the right-hand side. Well, to write a particular solution for this differential equation, what we can do, we can just take these two particular solutions that we have and then combine them together. So the particular solution for this differential equation, y sub p, can be written as, well, x squared plus 3x plus 3 e to 2x.